So good evening, everybody. So this is the third module of the HBNI online course on nuclear science and technology. I'm Dr. Umashankari Kannan, and I would like to introduce on something on fission physics. The contents of this lecture would be some basics of nuclear physics concepts, binding energy, the fission and fusion, and what is nuclear stability. And I would like to talk something about the radioactivity decay chains of uranium and thorium. I would also highlight properties of fissile and fertile material and exactly the mechanism of fission. So there is some critical energy which is required for fission to take place. So I will be highlighting those aspects. And then I will give a brief on the reaction cross-section. What exactly is the meaning of cross-section? What is the concept of cross-section? And then we'll go on to talk about the neutrons which are emitted in fission, whether it is prompt neutrons or delayed neutrons, and what are the neutrons, and what is the fission reaction. They are centrally charged, and the electrons are orbiting around the nucleus. If a nucleus is neutron rich, it is unstable and it can undergo fission. This process is called as a spontaneous fission. But if a nucleus is bombarded by a neutron, the nucleus breaks into small fragments. Actually, important is the stability for ions and forces. You know that nucleus is characterized by the neutron and proton. Neutron is massless, chargeless, and proton is positively charged. And here I have given you the mass of a neutron and mass of a proton in terms of AMU. And the electron is about 1,861 times lower than that of electron mass is 161 times lower, which also is 1 to the mass of the carbon atom. Now, what happens in the nucleus? Ions are present inside the nucleus and they are characterized by the short-range forces. A neutron can get converted into a proton or into a neutron. So all these processes are happening inside the nucleus. And that's where they're all, in terms for nuclear physics, it's called as nucleons. And they are characterized by short-range forces. Now, the big premise, the whole fission process is that it nuclear stability line, where we call this as the NZ plot. This is neutrons and number of neutrons. It usually follows this dark black curve. And on the left hand side, you have the beta minus decay, and the right hand side, you have the beta plus decay. So there are so many elements in the periodic table, which are because of these radioactive alpha or beta on. So the nuclear stability is dictated by N and Z nucleus. So it is defined by the ratio of the number of protons to the neutrons. So that is why it is important to see why certain elements are becoming radioactive. By emitting a beta, they become more stable, or by emitting an alpha, they become more stable, and why some of them are stable by nature and some of the magic numbers also you would be knowing. So this brings us to the topic of binding energy. Is not the sum of the masses of the neutrons and protons. So there is something called as a mass defect. This mass defect is energy, and that is what is binding the nucleus. So this mass defect is termed here as number of protons into mass of proton by number of neutrons, which is A minus Z, into minus mass of nucleus. So this is called as defect. The energy and equivalent principles, this delta M square would be the binding energy of the nucleus. Here I have shown you the binding energy of the nucleus as a function of atomic number, and here you can see there are some sharp Now, there are some sharp peaks which are basically the stable nuclei. This in the y-axis is called as the binding energy per nuclear having at this table is the iron 56, and here you can find that uranium 235 is somewhere here in 230, around 235 mass number, and so you would see that why fission is happening or why fusion is happening. Uranium 235 nucleus, when it neutron, it absorbs a neutron, it becomes U236 and it becomes unstable, and it splits into two fission products which are having higher binding energy. Thereby, it releases the energy equivalent to the difference binding energy of uranium-35 and its fission products. So the binding energy per nucleon is always positive. And the nuclear forces, you know by now, I have already explained to you that it is attractive by nature. So the attractive forces is more than the Coulomb repulsion of the protons. And so this is the curve which explains why fission is releasing energy, or in other words, fusion. Two light atoms can fuse also and give you the energy to become more stable. And there are, of course, peaks in when you talk about the shell model, and then it's very difficult to break the nuclei. And so these are magic nuclei. The linear difference of binding energy implies a saturation of the nuclear forces. So this saturation is closely related to the short-range forces. So if you have got clarity about this binding energy, you know that why fission or fission energy is going to be, or energy is going to be released in fission. So here you can see I have tried to explain it a little more. It's the most likely nature of the curve. So this difference is what is going to come out as the fission energy. Elements heavier than iron can yield energy by nuclear fission. And here, at lower mass numbers, this is a fusion of a DT fusion, deuterium and tritium, which energy realized is about 3.4 MeV per nucleon, and whereas in fission it is about 0.9 MeV per nucleon. So that is why there are 205 nucleons. This 90 to 35 200 MeV of energy is released in a single fission. Okay, so now we have got the idea of binding energy. Now let us say why fission is attractive. I have already told you that a uranium-235 nucleus undergoes fission, forms two lighter nuclei. Let us take an example. When uranium-235 nucleus absorbs a neutron, it becomes into two fission products and neutrons. On the right-hand side, the 134 nuclei average binding energy per nucleon is about 8.4 MeV, whereas in the left-hand side, we have 235 nucleons and the average binding energy is 7.5 MeV. So this results in a difference of about 0.9 MeV, which gives around 200 MeV of energy. So one fission of one atom of uranium-235 gives 200 MeV of energy, which when you calculate in joules, or it comes turns out to be 3.2 into 10 to the power of minus 11 watt seconds, or around 32 picojoules. Now just compare this with the combustion of one atom of carbon. One atom of carbon gives an energy of about 4 eV on combustion, and this gives 6.4 into 10 to the power of minus 7 watt seconds, or it gives you, if you look at the energy produced from 1 gram of uranium, you do the mathematics, you will get 80 terajoules, whereas the energy produced from 1 gram of carbon, or in other words, I have done statistics, it shows that you would require about 2.5 tons of carbon to produce the same amount of energy from a gram of uranium. I have tried to pictorially show this. This is a log scale in y-axis, and you can see 1 gram of uranium equivalent is giving you so much of energy, whereas 1 gram of carbon is giving you this much of energy. So that is why we are in business. So that is why fission is attractive, and you will be able to get more energy from unit mass of a fuel. let us talk again something fission. So how to explain this nuclear fission? Generally, we have used a liquid rock model to explain the nuclear fission. The nucleus is assumed to be in the form of a drop of a liquid, like a drop of a liquid. So a neutron requires some critical energy to cause fission in a nucleus. Let us say a neutron is absorbed by a nucleus, and it is somewhere here at the ground state of the compound nucleus. And because it's important, so here the energy of the neutron is such that it will be able to break this rock to imagine the surface tension of the rock, which is required by the neutron to break the nucleus, or this is called as the critical energy of the nucleus for the neutron. And here finally we get two products, and these are the different stages by which the fission process takes place. Now here you can see that the thorium-232, for example, the critical energy is about 7.5 MeV, and the binding energy of the last neutron is 5.4 MeV. So this is not enough to cause fission. So you have to have a fast neutron to cause fission in thorium-232. Whereas look at uranium-235. The critical energy which is required, which is difference, is about 6.5 MeV, and the binding energy of the added last neutron would be 6.8 MeV, and even so the case is uranium-235. Critical energy for and binding energy of the last neutron. Uranium-238, if you see, it's again even nucleus, and here you can see that it is 7 MeV is the critical energy for fission, and the binding energies. So by assuming that understand the fission process using the liquid of the nucleus, we can, which is required to cause this fission. A little more about the binding energy and the liquid rock model. There are so many terms, and this is how it defines the binding energy of the nucleus. The volume energy term, which is sheer volumes of number of, it is proportional to nucleons, and so it is proportional to 4 pi r square, or it is proportional to a to the power of 2 by 3. Then there's a Coulomb energy, which is the number of pairs dependent atomic number, and so this is another term which is giving the Coulomb energy. And there is an asymmetry part and a pairing part. So all these terms put together, you get the binding energy nucleus. So this each and every nucleus either a fission or a fusion. Little good talking more about. I already told you that some of the elements are either beta emitters or alpha emitters. So here I have tried to give you a natural decay of a thorium nucleus. Most of these are alpha emitters. Some of these in between you can see the beta emitters, and you get actinium-228 is called thorium. So a thorium fuel can be characterized by this gamma emitter, which is the natural process in the decay of the thorium isotope. And so that is why it is very, it's proliferation resistant fuel will come this much later. This is the natural decay of the thorium isotope. Most of these are alpha emitters, and you can see thorium has a half-life of about 1.4 into 10 to the power years. So this uranium-232 is produced in the reactor also, and it continues to decay, giving out this bismuth, and that is why when I'm using thorium fuel in a reactor, it is captured with this uranium 232 and the telltale signature from proliferation resistance. So the radioactive species is associated with thorium. That is why it's called as a proliferation resistant fuel. Now let us talk about the uranium decay chain. In the uranium, here you can see that uranium 235 is an alpha decay product of plutonium 239. Plutonium 239, these are all of course not found. Americium 243, and these are all produced only in the reactor. But here you can see natural uranium versus uranium 235. It's an alpha emitter, gives you 4231, and there are other products which are formed in the decay chain of uranium 235. So these alpha decays are characterized by the straight lines here, and the beta decays are characterized by the dotted lines here. And finally, you get a stable product like lead in the decay chain. So, but all these are what I wanted to impress upon you is, apart from being radioactive emitters, natural decay happen. This is a type of nuclei or the isotope. Now, let us talk a little about what exactly is going to be done fission process. Okay, we know fission process is taking place, but there is something which is important is the cross section for any particular reaction. Let us talk about a nuclear cross section. Let us try to find out the interpretation of what is a cross section. See, you all understand about reaction rate. Reaction rate is nothing but the cross section multiplied by the number of interaction. So here it is if R is a reaction rate, which is the interaction rate, I is the intensity of the neutrons, and N is the number of the nucleides in the target here. Now this reaction rate is proportional to the intensity and multiplied by the nuclear by a constant. This constant is called as a probability of a neutron nuclear interaction, and it is characterized by the microscopic cross section. This sigma is what is very, very important. It's called as a cross section for any particular type of reaction, and it can be seen as a probability or effective area offered by a nucleus or a typical type of reaction. Since this area is very, very small, we talk in terms of Fermi distances, which is the size of the nucleus. So the units of area also has to be very, very, very small. So the unit is 1 barn, which is 10 to the power of minus 24 centimeters square. This is the microscopic cross section. This is the property of a nucleus for a neutron of one particular energy. So they have different energies, different. I'll cover all that a little later. Now this is the microscopic cross section. We have another microscopic cross section. You consider a sample which is placed here, a beam of neutrons which is incident perpendicularly on the sample, and how much interaction takes place in the sample, and what is the net intensity of neutrons which is coming out of the sample, which is given by this I is equal to I naught into e to the power of minus n sigma t x. X is the thickness of the sample. N into sigma t is the total cross section of this particular target, and N into sigma is the macroscopic total interaction cross section. So a beam of monoenergetic neutrons which are striking the target, this N into sigma is called as the total probability of this particular target. And so the sigma t is called as the total probability, and this is the probability per unit length of small distance x here, at length, the neutron will interact with the nucleus. So this, if you take this unit, will be centimeter inverse. Now when you talk about this quantity which is e to the power of minus sigma t into x, it is a probability that the neutron will travel the distance x without making a collision, which means that much neutrons have come out of the sample. So it has not collided in the uncollided probability is given by e to the power of minus. Now the sigma t to exponential this sigma exponential e to the power of minus sigma t x dx is a probability that the neutron will collide in dx after traveling distance x. So this is the kind of the interaction probability which has happened with a monoenergetic neutrons, which is crossed, which is hitting a target, and it is causing interactions in this particular sample or target. So this is basically the microscopic cross-section or probability of a neutron-nuclear interaction, and this sigma is called as the macroscopic cross-section or the total nuclides in the sample or particular target. Something more about these microscopic cross-sections. In order to find out the net interactions in a material M, we need to know the number of atoms and the interaction rate. So this atom density of any particular target is given by, the Avogadro's number rho, Na, and rho is the density of the sample, and M is the molecular weight of the sample, and Fi is the fraction of atoms of that particular type in a molecule. So this is the total atom density of in a sample, which is given by Ni is equal to rho Na by M into Fi. So now this Ni will be the number of nuclides in a particular sample, and if this is multiplied by the microscopic cross section, we would get the macroscopic interaction cross section. Example, I'm giving you some I'll give you some assignments also in which you can calculate density, but here I'm trying to impress upon you what would be the atom density of uranium-235 or uranium-238 in a natural uranium fuel, and how to go about it. 18.6 is the density of natural uranium, and this is the Avogadro's number, this is the molecular weight, and this is the weight fraction of uranium-235 in natural uranium, which is 0.7%, and so we get around 3.3 into 10 for natural uranium sample. Similarly, the uranium-238 would be 4.67 in 10 to the power of 22. Similarly, I can calculate for a mixture of light water and heavy water. Here I've taken an example of light water as 0.2% in heavy water of 99.8, and how I have found out the atom fractions. I can leave this presentation with you so that you can see all these later, but basically you can calculate the number density of each and every component of the fuel or the coolant or the moderator which is being used. So here in this case it is oxygen or hydrogen or deuterium. You can calculate an atom density for each and every mixture. Now I was telling you about interaction. So now this interaction is also what is more important is what is the mean free path for interaction. I was telling you that it is collided and uncollided. It is collided. What is the interaction rate? Now, if I talk about a probability of interaction, I can define an average distance which is a neutron can travel before interacting with the nucleus is given by, let's say, x bar. The probability of p of x dx. If I integrate it from 0 to infinity, I can I can reduce it to sigma t into dx x exponential e to the power of minus sigma t x. So this is nothing but 1 by t. Sigma t is the total cross section interaction, and this total cross section 1 by sigma t can be thought of to be as a mean free path of interaction. See, that is a neutron traveling in a sample. A beam of neutrons are traveling in a sample, and what happens is that what is the mean free path or mean distance over which this interaction can take place. For example, if it's a very strongly absorbing medium, and if you consider it for D2O, the scattering mean free path is 2 centimeters, whereas the absorption mean free path is 30,000 centimeters, which means it's a very, very, very weakly absorbing medium. And that is why we use heavy water in the thermal reactors as a moderator. In graphite, again, you see that the absorption mean free path is 3600. Oxide, which is used as a neutron absorber for thermal neutrons. Here you can see that the mean free path for absorption is very small. That means it's a very, very strong absorber. What I want to impress upon you here is that what the nuclei will interact with neutrons in a different way. And so that is why these cross sections are important, and that is why we now let us talk something more about the neutrons. You know, in a fission reaction, neutron is getting absorbed, a compound nucleus is formed, the compound nucleus splits into two fission products and also produces some neutrons. Now there are different types of neutrons which are being produced. The neutrons which are being produced at the instant of fission is called as a prompt neutron. There is an instant of about 10 to the minus 50 seconds. For example, fission of uranium-235 on an average uses 2.5. You have studied textbooks. So 2.5 neutrons are produced in every fission. But what is the spectrum of these neutrons? You can see if the prompt neutrons would have, which is peaked at around 2 MeV. So from 10 MeV to around 2 MeV or 1 MeV, you have these neutrons which are being produced, which are fast produced as an instant of fission. But also there are some neutrons which are going to be produced after some time. Like I told you, you saw that lanthanum and bromine were two fission products. So these fission products are neutron rich, and they would become stable by emitting a neutron. So these neutrons are produced after some time depending upon the half-life of that particular fission product. And so these neutron-rich fission products emit neutrons after a few seconds of fission. Called the stable, which are different species of fission products. One is that longest half-life is 55-second half-life. This is a Kannan one, which gives you about, this is a fraction, and this is the energy of the neutron. Here the energy is about 2 MeV, whereas the energy of the delayed neutron is of the order of keV. So there is a spectrum here also. So on an average amount of neutrons is going to be neutron fraction. 235 with thermal neutrons. This delayed neutron fraction is about 0.0065. So here I wanted to impress upon you, there are some neutrons which are being produced in a fission process. One is a prompt neutron, which is being produced at the instant of fission, which is has a which is emitted at 10 to the power of minus 15 seconds, and delayed neutrons, which is emitted after seconds after the fission by the fission products which are neutron rich. Now let us talk about the energy of the fission. I have told you on an average, because of the difference in binding energy, we get 200 MeV of energy. Now let us see how this energy is distributed in a fission process. What are all the things which are happening? Fission products which are being produced, the fission fragments are moving away in different directions because of the liquid drop of model. Liquid drop model, you see that the two fission products are separating out. So the kinetic energy of the fission fragment will carry away most of its and most of the energy. That is 80% of the energy produced fission fragments is gamma rays which are being produced. This is around 7 MeV. The neutrons also having kinetic energy, that is around 5 MeV. There are betas, neutrinos, then gammas from fission products, betas from fission products. All these are also giving you around 7 to 6 to 10 MeV. Total about 200 MeV is being these different aspects of the fission. So the kinetic fission factor of the energy, which is about 170 MeV. But this is 200 MeV is called as the Q value of the fission reaction. I was telling you about delayed neutrons, and then we have categorized the delayed neutrons into different categories based upon its half-life. So in general, we consider six main groups of delayed neutrons, which are based on the half-life of the delayed neutron precursor. Now here, this is a 55 half-life, the 23 is 6.2, so on and so. And here I have tried to impress upon you that there are different fissions which is happening in different fissile nuclei. One is uranium-233 or uranium-235 or plutonium-239, and the fraction of delayed neutron from the precursor for each of these fissions are going to be different. This is playing an important role in reactor control, which we will learn later. So in uranium thermite, which is 0.0065 the fraction of delayed neutron, whereas plutonium fission, this is 0.0020, which means delayed neutrons in a plutonium fission. So when plutonium fuel is being used, you have to be very careful in seeing that you don't get a situation where you are not able to control the reactor. We'll come to that a little later. And these are all the energies of the delayed neutron. There is a delayed neutron precursor, which is the fission product. These fission products become stable by emitting a neutron. And they have an energy particular in the energy levels of the ground state and the excited state of the fission product. And now we were talking about neutrons, we were talking about the energy in a fission. Now let us talk about process. We need neutrons to cause fission, we need neutrons available, and we need to produce these neutrons. So how do we produce these neutrons? The most important neutron sources are the comes from the interaction of alpha. So the alpha emitters, they give a neutron in the following just by the following reaction here. See, for example, there is a radium beryllium, americium beryllium, or polonium beryllium sources. So the alpha from the americium will interact with the beryllium and give a neutron. So this is the reaction which is taking place for production of neutrons. Alpha emitters with long half-life are actually suitable. For example, polonium has a half of 138, it's low, whereas americium has 433 years. So we generally use an americium beryllium source as a source of neutrons. And these neutrons are also of the order of MeV, and they have a spectrum, of course. So this americium alpha particles interact with low mass element and produce neutrons. So these are the different types of neutrons, these are different types of neutron sources which can be used sometimes for a reactor start to initiate the and also neutrons. It's another source of neutrons. For example, gammas, when interact with deuterium, give away a proton and a neutron. This is a very famous reaction by which we know that to have a 2 MeV of energy, only then it can break the deuterium bond, and thereby, so this photon energy has to be of 2.2 MeV, and we get a neutron of this of neutron from this reaction. That is why we say sources in some of the heavy water reactors, because neutrons are always available and will interact with the heavy water and give you some neutrons. Similarly, beryllium can interact with the gamma and give an alpha and neutron. This is another source of neutron, which is a photoneutron. So these are all some alpha end reaction based or gamma end reaction based neutron. But also there are some high energy neutron generators which are based on fusion. For example, DT generators and DD generators. Due to two deuterium atoms will fuse together, give a helium-3 atom a neutron of 2.45 MeV. This is a famous fusion reaction. Similarly, but this fusion reaction can be used as a generator of neutrons, of high energy neutrons. Similarly, there is a DT fusion, that is deuterium and tritium. They will interact, they will fuse together to give a helium and a neutron of 14.1 MeV neutron. So these are high energy neutron generators. Now, I was explaining to you something about giving you the diagram of how exactly uh, the delay is produced. There is a Brony 7 which is having a 5-second half, and then it would decay to krypton 87 by emitting a neutron. This neutron is the energy of the krypton 86, 87. And so energy of about 0.1 to 0.4 MeV, which is an order less than that of a prompt neutrons, is being generated. And why it goes to krypton 86? Because it's a magic number. It would like to become stable and come to a stable configuration. The second group, 77, this is a it would decay to that particular isotope. So basically, these are how the delayed neutrons are produced because of the neutron-rich fission products. Similarly, I was talking to you about fission gammas. There are gammas which are being produced in these fission is also having a particular spectrum. This is from gamma rays, and delayed gamma rays is about 7.5 MeV per fission. So it has some sort of a spectrum like this. So there are gammas which are being produced in fission. There are neutrons which is being produced in fission. There are neutrinos. There are beta particles. All these things are produced in fission. So we bother about these neutrons and gammas because we need to track these neutrons. The energy we go towards the to electrical energy conversion to the structural materials or your water or your moderator and so on. So we should take care of these things, and we should account for the amount of heat which is being produced by the fission gammas and the fission products and the fission product B and the other particles. And the energy is the mechanism of fission. What is meant by number density? What is meant by mean free path of interaction? And how the prompt neutrons and delayed neutrons, what is the difference between the prompt neutrons and delayed neutrons? How are they produced? Then why some nuclides are radioactive, and what are the decay modes by which they decay, whether it's alpha, beta, or gamma. What we have studied, these neutron sources can be used to produce neutrons. So I think I would stop sharing.